Hello. Welcome to Optimizing Measurements. 9.5, maximize the volume of a cylinder, and 9.6, minimizing the surface area of a cylinder. Now, a cylinder is essentially a can, like a Coke can or a can of tennis balls, any sort of can that's circular on top and then kind of flat around the middle. So if I have some sort of radius r, that radius will be equal, or the height of it, the can, will be equal to 2 times that. So 2r will equal the height. That will give me the ideal conditions to either have a maximum volume or a minimum surface area. The surface area will have a formula of 6 pi r squared, so 6 times pi r squared, and the volume normally is pi r squared times height, will actually change to now 2 pi r cubed, because now we've just multiplied that height by another r, so now it's cubed, and we have another 2. So let's take a look at a couple of examples for these types of equations. I want to know what are the dimensions and the volume of a can of soup made from 860 centimeters squared of aluminum. So I have this surface area, and I want to know the dimensions and volume of this can of soup, and I want the maximum volume. So the maximum volume that I can put in this, or the maximum amount of soup I can put in this can when I'm done with it. So I know that SA, my surface area, is equal to 6 pi r squared. So I'm really looking for r in this case. It's the only real measurement of note. So I have 860 equal to 6 pi r squared, and I'm just going to divide both sides by 6 pi to isolate r squared. 6 pi. So 860 divided by 6 equals 143.33, and I'm just going to divide it again by pi. And I'm going to get 45.6, and that's going to be equal to r squared. Square root both sides, and I get 6.75 as my radius. That's great. So I figure out the volume. Volume is equal to 2 pi r cubed, so 2 times 3.1459, etc., times 6.75 cubed, or 6.75 times itself 3 times. So I have 2 times pi times 6.75 times 6.75, and again 6.75, and I get a volume of 1932.4, in this case, centimeters cubed. So that's a maximum volume that I can make from that amount of aluminum, which is quite a bit for a can of soup. My next example, I want to determine the amount of plastic needed to cover a cylindrical water tank with the volume of 7,340 meters cubed. So this is one of those big water reservoir tanks. I want to know how much plastic I'm going to need to cover it, because I'm going to have to keep it away from other chemicals and kind of seal it in. So now I'm going, in this case, since I'm trying to find surface area, because that's essentially what I'm looking for, I have to look at volume to find the radius. So I have volume is equal to 2 pi r cubed.
Line 101, please.
So I take my volume and I substitute it in, 7340, 2 pi r cubed, divide both sides by 2 pi. So 7,340 divided by 2 divided by pi. And I get 1168.2 equal to r cubed. From here, I take the cubed root, like that, and I get a total of 10.5, give or take, equal to my radius. So that's my radius. I then take that number and plug it into my surface area formula. 6 pi r squared for these maximum minimum values. So surface area 6 times pi times 10.5 squared, 6 times pi times 10.5 times 10.5 gives me a surface area of 2,078.2 meters squared of plastic needed to cover my water tank with a volume of 7,340 meters squared. So I've combined two lessons into one, but they're essentially the same idea. So if I'm looking for surface area, first I have to find the radius, and I use that with my given volume formula. Before, I was given the surface area and I wanted to find the volume, so I used my 6 pi r squared formula to find the radius and do the reverse. So these are two lessons that are very much intertwined, and that brings us to the end of optimizing measurements.